Hi guys, welcome back. Today is October 6th. Once again, let me not forget, happy October. The learning target we have for today is I can identify a phase change in matter by analyzing a heating and cooling curve. So where we left off yesterday, we are continuing with today, and it's exactly the same material. So let's go ahead and get started. So this is our do now. I want you to take the next 2 to 3 minutes and go ahead and complete it. And this is just basically reading the heating curve that we just had yesterday. Now the thing I want you to do is anytime you see a heating curve, you must label it automatically. Automatically. Go ahead and label it. And like I told you, each line segment represents something that will never change. No matter what the substance is, it will never change what the line segment is. But right now we're going to be dealing with water. You're going to notice we're going to be dealing with water a lot. So go ahead, take the next 2 to 3 minutes and do the do now. You can pause me and then come back. So at this point, I assume you've paused me and you've come back. So let's go ahead and let's do this do now together. Right? So like I said, the moment you see a heating curve, I want you to go ahead and label it. So when I label it, I know that all my slants in a heating curve, anywhere I see an increase represents a state of matter. And states of matter always begin with solid. So this would be solid, this would be liquid, and then this would be gas. And then I ask myself, how do I get from a solid to a liquid? And then I always use the example of water. So if I have ice, how am I going to get to liquid water? And I would be melting. Right? And then when I have liquid, how do I get to gas? I would be boiling. Yes. So, or if you want to call it vaporization, not evaporization, but vaporization, that is fine as well. Sorry about that. So, here we go. So we know what each state of matter is, and we know the phase changes, how we're going through each state of matter. So let's go ahead and answer the questions. I want you to do this every time. Before you answer any questions, label the diagram. It is very helpful and useful. At what temperature would the substance be boiling? So you see, by just labeling it, we already know where boiling is going to occur, right? So anytime you label before you actually solve the problem, you've already kind of done the work for yourself. So I'm going to go ahead and look for, I know boiling happens at this line segment here. So I'm going to take this line segment and go all the way to my left. And I notice that that's happening at 90 degrees Celsius. So at what temperature is the substance boiling? It's going to be at 90 degrees Celsius. All right. Now, at what temperature would the substance become a liquid? Now, they're telling me what substance do I become a liquid. Now, thankfully, I labeled before I even started my problems. So I know that liquid is this middle line segment here. So, but I know that liquid doesn't start over here at this point. Liquid starts at this point right here. So it sets for the temperature. So at this point right here, which is also my melting point, I'm going to take it all the way down to the side, to the left, and that's going to be 50 degrees Celsius. For some of you who are a little bit confused on how to read this graph, what increments it's going on the side, just go ahead, always just experiment, start with 0 and see. We know that it's every few ones are 30, so find out how much it has for each little box. All right. So like I said, today we're going to be focusing on this diagram a little bit more. There's not a lot of graphs in chemistry. This is the only graph that we truly deal with. So let's go ahead and move on. And like I said, each component of this graph never really changes. So I want you to take the next 4 minutes, read and answer the text related questions. And go ahead and pause me at this point and go ahead and do that. And then unpause me and we'll get started. So I assume at this point, if you unpaused me, that you are done reading and you've answered your text-related questions. So let's move on. Like I told you before and yesterday, I know we didn't really outrightly state it, but sublimation is when we go from solid to gas, just like so. All right. The perfect example we have of this is dry ice, and then we also go from gas to solid, like so. And another example, and that same example would be dry ice. There is no middle phase for dry ice. There's no liquid carbon dioxide. We only have it in solid and in gas form. So, sublimation, we're skipping that middle step. Sublimation and deposition, we are skipping that middle state of matter, which is liquid, and we're going from solid to gas instantaneously, which is sublimation, and we're going from gas to solid instantaneously. That is deposition. So, like I told you, with our heating curve yesterday, it is very simple to go ahead and label a heating curve. We're going from solid to gas, but it's reversible. If you said yes, it is reversible because we can't go from gas to solid, you are correct. So this would represent our heating curve. So I want you to go ahead and label each component. Leave boxes 2, 4, and 6 alone, but go ahead and tell me what 1, 7, 3, 8, and 5 represent. Go ahead and take a few minutes, and then we'll talk about it. So, if you said that box 1 represents gas, you are correct. If you said box 3 represents liquid, you are correct. And if you said box 5 represents solid, you are correct. This is a cooling curve. So instead of us now increasing our heat, we are decreasing our heat. So our particles are now becoming more compact. Now, how do we get from gas to liquid? Well, we are going through condensation. We already discussed this a little bit yesterday. And then how do we get from liquid to solid? We are going through freezing, right? So, we're still going through our states of matter, but this is a reversible process. So we're still talking about physical changes because our substance still remains the same. We're just changing the way it looks. Now, obviously, I wanted to show you guys what a gas particles looks like. So gas particles are all loose and free. They do not have a defined shape or volume. While volume are a little bit compact, they do have a defined shape, volume, but no defined shape. And then we have solid, which has a defined shape and a defined volume. To go about this. Now, this is a cooling curve. I'm going to say this again. This is a cooling curve, not a heating curve. So, heating curve, we see an increase in temperature. Cooling curve, we see a decrease in temperature, right? Where our substance becomes a little bit more compact. Think of you're taking steam and you're creating ice. So let's move on. So I want you to take the next 4 or 5 minutes and go ahead and read the text-related questions, and then come back to us because there's one more thing that the heating and cooling curve tells us, and hopefully you'll understand it a little bit more once I explain it. So go ahead, pause it, and then come back. So hopefully you've paused this and you've read and you've answered the text-related questions. We need to know our definition, so it's very important that you do the reading and you understand some of the terminology that we're going to be using. So, I want you to use that information that you learned in the reading and apply it to the curve. Give yourself a little time, refer back to the reading and apply it to the curve. I will explain it, but go ahead and try. This is all brainstorming to see if you're able to apply what you read to the content provided. All right. So here we go. Now, what you just read about was about kinetic energy and potential energy. Now, kinetic energy is the ability to move, right? The energy needed to move. So anytime we're talking about any type of movement, whether it be physical or theoretical, we are talking about kinetic energy. Now, potential energy is having that stored energy, having that energy to do something, the potential to do something, the ability to do something, right? So, with potential energy is more stored energy. We're gaining the power to do something. And then kinetic energy is actually doing that act. So, if you are I don't want to say stretching because you're actually moving. Um, if you're like relaxing, you're relaxing, you're relaxing, you're relaxing, you're relaxing, and then all of a sudden you start running, you relaxing was you storing up potential energy, and then you running was exerting your kinetic energy. When you go on to physics, you learn a little bit more about that. But as of right now, the stored energy, you absorbing that energy, you storing it for something, its potential, and then the movement, the actual conducting of that act would be kinetic energy. Now, what happens is that what I just said, kinetic and potential energy can be applied to the heating and cooling curve. And I want you to think about where in the cooling or heating curve will you see kinetic energy. Remember, kinetic energy is movement. Movement. So where would you see energy? Where would you see movement in the heating and cooling curve? Give you a second to think about that. So if you thought about maybe it's happening when the temperature changes, you are correct. Anytime we have a temperature change, we have kinetic energy. Every time we don't have temperature change, we have potential energy. Hopefully that makes it a little bit easier to understand. Anytime we have temperature change, we have kinetic energy. And then anytime we have no temperature change, we have potential energy. So let's go ahead and label this graph to tell us where we have kinetic energy and where we have potential energy. I'm going to use KE to represent kinetic energy and PE to represent potential energy. So we have a movement in the first line segment. So that would be kinetic energy, where number one is. And then where else is number one replicated? Well, we can see that at, we can see that at 3 and 5. So we can assume that anytime we have a slant, we have kinetic energy. And then where do we see there's no change in temperature? There's none whatsoever. If you said 2 and 4, you are correct, right? So for somebody who, if you're thinking a little bit more farther ahead, you can say kinetic energy is where we have our states of matter, and then potential energy is where we have our phase changes. Now, if that's a little too complex for you to think about, then also just think about this. Where we have temperature change is where we have kinetic energy, and then potential energy is where we don't have temperature change. So go ahead and create your shortcut. My shortcut would be the platforms, right? The platforms where I have potential energy and phase changes. And then the slants, where I see a change in temperature, is where I have kinetic energy and states of matter. So I want you to go ahead and use this and practice. Practice, 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 all right? We're going to be practicing this again tomorrow, but it's very important that you're able to tell us and read a heating and cooling curve. Half of the job is reading and understanding a heating and cooling curve. All right, if you have any questions, please feel free to reach out to me or Mr. Schwartz. We are most definitely here to help you, and I hope to see you during the live Zoom sessions today. All right, have a great day, guys.